Okay, then we calculated the temperature and pressure and specific volume at each state. Then how can we use those values to calculate real things that we really want to know, like how much work can be done from this engine and what is the thermal efficiency of this engine as well. Okay, so let's try to calculate the work and the power first. Then, all right. So there are two types of work in the engine process, engine analysis. One is indicated work. The other one is brake work. The indicated work is the work involved in the cycle analysis. Okay? So from the cycle analysis, based on the volume change and pressure changes, then how much work actually can be expected, I would say. The brake work is more realistic work. Even though you can extract that much of indicated work out of an engine, but this engine is not operating by itself. This engine is connected to crankshaft, right? And now that is connected to other parts like tires and other shafts. So the brake work discusses how much work actually can be extracted from the whole power assembly. Okay? And I'm gonna revisit that brake work just a minute later. But let's talk about the indicated work. So again, indicated work is based on the cycle analysis. Okay? So the indicated work, or in the case, net work, okay, that is produced by the engine per cycle, can be calculated by the expansion work minus compression work. Okay? And each work can be calculated from the process 1 to 2 and 2 to 3 to 4 based on this old thermodynamics. And by having those numbers into this equation, for the specific engine, we have 0.909 kilojoules. Okay? But what you have to remember is that this value is the amount of work that is produced by this engine per cycle. Okay? Now I'm going to use this one when you try to calculate the power. Okay. So before we go over to talk about the power and efficiency and so on, let's briefly discuss the mean effective pressure, because the mean effective pressure is more relevant to the indicated work. Okay? Many times, in the automobile companies, they love to use mean effective pressure, or in short MEP, than the work, the number itself, because MEP gives us a more intuitive value of how this the engine performs in terms of power output, right? So let's take a look at this slide. The mean effective pressure is defined as a fixed pressure that would produce the same amount of net work during a constant pressure process. Then we have this equation. So we have to use this equation, but I'm gonna move to the whiteboard to explain more about why and how we get that equation based on the statement about the MEP definition. Okay, so now we came back to the whiteboard, and now we can calculate this net work. Okay. But many times, as I said, we can use MEP instead of this net amount of work, right? Now, from the statement I just showed you in the slide, the MEP is the fixed pressure that, by assuming that, okay, so how much we can produce this net work if we assume that entire process is done under the constant pressure process. Okay? And now, if we have constant pressure process, your work, which is boundary work, by the way, so boundary work can be calculated by pressure times V2 minus V1. Here V2 and V1 is the initial state volume and the final state of volume. So instead of P here, we use MEP because again, now we assume that if your engine entirely operates in terms of constant pressure, okay, then now your volume changes from the minimum to maximum here. So V2 should become maximum volume and V1 should be your minimum volume. Okay. So if you are given those design parameters like, okay, so in terms that Vmax and Vmin should be related with your design of engine, big, small, such as those kind of geometries. But if you decide that kind of geometrical limitations in terms of maximum volume and minimum volume of your cylinder or your piston movement, then in order to produce that much of amount of net work, how much mean effective pressure should be achieved? So that is main, the main motivation. So from that equation, what it can write in terms of MEP is so now the boundary work can be replaced by net work. So net work divided by V max minus V minimum. Okay? Or we can write the same equation in terms of all values per unit mass. So instead of capital W net, we can have small W net, which is the net amount of work per unit mass divided by specific volume max minus specific volume min. So again, the specific volume is the volume per unit mass. So we can calculate this MEP from this equation. Now, why is that important? Why many car manufacturers love to use MEP instead of the net amount of work? Because if you think about the two engines, one engine is really huge, okay, like pickup truck, and the other engine is quite small for compact cars. Okay, then you want to compare which one is better. Then obviously, if you just look at the amount of work between these two engines, you have to always make a conclusion that the engine for pickup truck should always better, because now obviously because that engine is much bigger, should be much bigger than the compact car engine, then as a result this engine must produce more work, right? It's really kind of natural to think about it, but is it really so? Now, so that's why, sometimes you have to compare engines with different sizes. And only by using the amount of work from those engines, cannot make us make a good decision about whether or not, which one is better in terms of power output. But if you really convert that work, net work, to mean effective pressure, everything can be converted to kilopascal. So the unit of MEP is just unit of the pressure. So we can kill all the size dependence of that engine. Then by using MEP values, it doesn't really matter whether your engine is big or small. As far as you can take a look at the MEP values, then you actually can see which one does give you more power or more work, okay? Considering that size. So that is why the MEP is so attractive for us to use in terms of talking about the net amount of work of that certain engines. Okay. Then we can calculate it, right? We already calculated the net work, and we know Vmax in the case it should be V1 or Vmin, that is V2. Okay. Or we can calculate the net work per unit mass by dividing the value that we calculated with the mass of working fluid we also know about. And we know this passive volume at 1 and passive volume at 2. So we can calculate this MEP for that specific spark ignition engine, and that gives us 570 kilopascal. Okay, by only looking at that number, you know that is pretty hard for you to evaluate whether or not this engine is good. But that MEP, works fine, works pretty well when you try to compare two types of engines.